suppose you have written a word made, and I want you to convert it into make. In a Microsoft Word, you have written made, and I want you to make it make. So there are two ways. Either you delete the whole word made and write make again, make, and another way, just you delete D alphabet and write K alphabet at the same place. In both the cases, would it make difference? Absolutely no. Either you delete the whole word and rewrite it, or just replace one alphabet by another alphabet, it makes absolutely no difference. So using this analogy, I would like to make a point that thinking about any fundamental particle like electron, proton, neutron, talking at the basic level, these are the fundamental particles, and these fundamental particles are same. Either you talk about take a rock and analyze them, and you go inside my brain and look at some serotonin molecule in some neurons, and if you go and look at these fundamental particles, electron, proton, neutron, same everywhere. So let's assume that and hypothetically somehow you get an ability to exchange your fundamental particles with another thing, and let's say you are exchanging your electron and proton and neutron one by one with a rock of the same size, and so it makes no difference, basically, because electron is electron, doesn't matter where it is, even if it is in rock, and it can go in your body and do the same work like the way what an electron does. So if you are if you keep exchanging electron, proton, neutron with a rock, then at what moment you would say that you are rock and rock is you, or vice versa? That is a big question, but today I'm not going to talk about this. We'll talk about this in the next some series, but today I'll continue the same that I started talking in Protein Saga series. So in order to understand protein, today I'm going to introduce you a methodology which is very important that I do regularly, like now also I'm doing it, and so I thought to just explain you this methodology, and this methodology is basically an optics application to study any kind of macromolecules or biological system that have been developed in our past few years. So the name of methodology is FCS, Fluorescence Correlation Spectroscopy. So just to introduce this methodology, and I'll talk in very simple terms, just so that I'm talking to you, you guys, and I'm aware of the fact that going in detail is not really needed. The purpose of making these video series is to inculcate scientific attitude in people who are really interested in science, that how do scientific experiments happen, how do whatever you read in your textbooks, from where, and how it a rule become rule, a law becomes law, what are the experimental ways to get a law, and then you read it in your textbook. So to introduce this methodology called Fluorescence Correlation Spectroscopy, so I'll use my fundamental way to teach something. To what is fluorescence spectroscopy, I'll just fragment it into three parts. There's a fluorescence, there is a correlation, and there is a spectroscopy. I'll introduce one by one. So first thing is fluorescence. What is fluorescence? So fluorescence is basically optical property. Optical property means light property. And can you see me? Of course you can see me, because some light is coming from your screen, and then but when you're looking at me on your screen, essentially you are seeing an image or whatever is running on your screen. But how can I see or how can anyone see an object? So basically light falls on that object, and that reflected light goes in our eyes, and in eye some and retina some image formation happens, and those image formation, there are some neurons that goes to the optic lobe of your brain, and there are some analysis happens, and brain has an ability to give different color to different wavelength, and it has memory also. So by that means you can see an object. So reflection is a property. In the same way, there are other light optical properties like scattering is a property. So what happens when light falls an object? It gets scattered. Scattering means when light and particle collide with each other, they just change in direction, and such that sometimes the light which is falling on the object and light which is deviated from its path, we call it scattered light. So this collision can happen. If it is an elastic collision, then it will give you wavelength of same, scattered light will have same wavelength, and if it is inelastic collision, then you have different wavelength. So you must have heard about Raman scattering. So Raman scattering is our great C.V. Raman have discovered this phenomena, the Raman scattering, and every particle has a classic scattering or optical property. In the same way, there is one more optical property we call absorption. So if there is an object and light falls on it, it has an ability to absorb some light of it. So basically, when I say that light gets absorbed by a particle, where does it go? So essentially, to understand this, to develop this insight, that where does light go, we need to understand light in a particle. So at the bottom level, at the basic level, when I say particle is made up of whether it is molecule or compound or anything, it is made up of atoms. An atom is nothing but we have some a proton, neutron in the nucleus tightly bond with each other, and there are electrons, considering it a particle now, and it keeps on moving around the atom. So what happens that when light falls on atom, it just goes, it gets absorbed by electron. And what is light? Light is it's not a very if you think in detail, it's not very easy to define light, but one can define it in a two way. One way, one can call it light is a wave. It's a part of electromagnetic, it's a electromagnetic radiation. It has it has wave property, and it acts like a wave, and it illuminates something. And second, various theories says that it's a light is a particle, and it has a lot of photons in it. Now, photon is a particle, small electron energy packets. Photons are so these discrete packets of energy people call photon, and this is well proved by Albert Einstein's photoelectric effect phenomena, that how light behaves like a particle in its photoelectric effect, that there is a metal, and when light falls in it, the electron gets ejected from the metal. And reason is of course my Takiya Kalam, that reason is very simple, that metal has apparently bigger size, and if it has a bigger size, then distance of electron from nucleus is more, and the nucleus has if an electron is more at a more distance from nucleus, then it has more energy, and since it has more energy, it is less stable, and also the affinity of nucleus or electrostatic interaction between nucleus and electron is weak. And when light falls on it, light gives basically this energy gets absorbed. Light is energy, so this energy gets absorbed by electron, and it just emits. In the same way, when absorption happen, when light falls in an object, so this light energy absorbed by the electron, and this electron jumps from inner shell to outer shell, because electron has more, if electron has more energy, then it will revolve in outer shell. If electron has less energy, then it will revolve near the nucleus. And at the end, if electron has gained sufficiently energetic photons, then it will leave the atom and it will go out. So this is absorption. So in the same line, this phenomena today I'm going to define is fluorescence. Fluorescence is also an optical phenomena that is mostly observed in a particular kind of molecules. We call them fluorophore. So these fluorophore are typically rich in pi electrons. It has aromatic ring-like structure, and these aromatic fluorophore, so when I say aromatic, essentially I'm talking about the pi electron which is doing certain stuff. So, and since these pi electrons form by sidewise overlapping, there are two kinds of covalent interaction that can happen in nature. One is the main overlapped electron that forms the strong sigma bond, we name it, and another is pi electron, and pi electron forms by sidewise overlapping, which is loosely adhered to the nucleus, and it is less stable. So when a fluorophore which has pi electron, they absorb some light, some photons, then what happens? So as I said, that it goes in some excited state. Okay, and let's talk about some. So fluorophore can be of different type. If it is intrinsic fluorophore, then it will naturally found inside your cell, like NADPH is a fluorophore. Like chlorophyll also sometimes show some amount of fluorescence. So in protein you have tryptophan, tyrosine, phenylalanine. These aromatic amino acids they show great fluorescence in ultraviolet range. And there are some other fluorescence that you can observe even in the visible range, like you have oxygen dye, you have ato molecules. So these molecules are basically pi electron rich molecules, aromatic molecules, and these, if you excite these molecules by a suitable wavelength, then what happens, that the electron from ground state gets excited to the excited state, and it remains there for some time in the excited state. It relaxes. So even in the excited state, so when I say ground state and excited state, these are different energetic states of any particle, either electron, proton, neutron, atom, molecules. Even I am having different states. When I sleep, I'm having low potential energy. When I am standing in a standing position, then I'm having high potential energy, MGH, because H is high. So similarly, even in ground state and excited state, there are multiple substates. We call them, different vibrational states. So electron moves around the nucleus, as well as it has some rotations. It vibrates because of thermal energy and a lot of other things. So what happens when you excite fluorophore by a suitable wavelength of light, then it goes in excited state, and in excited state there are multiple vibrational states. So let's say that excited state, I'm naming it by ES. So there are ES1, ES2, ES3, and ES4, and when you excite an electron from ground state to excited state, there are multiple smaller states in the excited state itself, and it takes around femtosecond to excite an electron from ground state to excited state. So you excite the fluorophore in femtosecond time, and then it remains in the excited state for some picosecond, and then it comes back to the ground state in some nanosecond time scale. So what happens, that when it comes back, so as I said, that you excite the electron to the excited state, and from the excited, so there are multiple vibrational states in the excited state, and it relaxes to the excited to the lower vibrational state of the excited state, and from that lower vibrational state of the excited state, it relaxes to the ground state. It comes back to the ground state. So when an electron comes back from excited state to ground state, it releases some photons, and that photon we call fluorescence. So so there's one important thing to mention here, that when you when I talked about the vibrational relaxation, that doesn't matter where you excite your electron, in which vibrational state of excited state, it ultimately relaxes to its lower excited state level, and from that level it relaxes to the it comes back to the ground state, giving you fluorescence light. So one thing that is important to understand here, that when this vibrational relaxation happens, basically you radiate some energy in form of heat, and in any kind of non-radiative processes. Non-radiative processes means a loss of energy other than the fluorescence process. Okay, so there is one more thing that need to be discussed, and that thing is called Stokes shift. So basically, when you lose some energy, by some non-radiative means, essentially your energy of the electron has been decreased in the vibrational relaxation phase. And then what will happen? When electron will come back from excited state to ground state, energy of this released photon will be lower as compared to the photon that was fallen on the fluorophore for the excitation. So that light we call excitation light, and the light which is coming out from the atom or the fluorophore, when electron is coming back from excited state to ground state, so energy of this fluorescence, that we call fluorescence, so energy of this fluorescence light is lesser. So, and how do we generally define energy? Energy is hc by lambda. Lambda is wavelength. And if energy is lower, then definitely wavelength will be higher. So what happens, that is called Stokes shift, that excitation wavelength is higher and fluorescence wavelength is no, I said other way around. So excitation wavelength is higher, and fluorescence excitation wavelength is lower, and fluorescence wavelength is higher. So that is we call Stokes shift. Like if you take excitation spectra and fluorescence spectra will be shifted. When I say spectra, means you are looking at any property, excitation wavelength, fluorescence, or absorption at different wavelengths. Spectra is measuring something at different wavelength. So this is what we call the fluorescence. Fluorescence is important because as I said that this electron remains in excited state for some picosecond time scale, and this time is sufficient enough to interact with the different thing that is present in the surrounding, and a lot of other things. So there's a fair chance that it is truth that what happens, that when environment changes, fluorescence property changes. So let's suppose there is a protein which is folded, okay, and you are looking at the tryptophan fluorescence. So there is a tryptophan. So tryptophan is a hydrophobic amino acid, and if a protein is folded, most likely tryptophan is buried inside, because hydrophobic things would like to dissociate it from water. Like if a protein is folded thing, then on the surface there will be hydrophilic amino acids which will interact with water, which is polar thing. Hydrophilic is polar and water is polar, so polar will interact with polar, and hydrophobic amino acids like tryptophan, like tyrosine, like phenylalanine, these hydrophobic amino acids will buried inside the protein, and so the fluorescence of this tryptophan will be different when it is folded and versus when it is unfolded, because when it is folded, the environment around this tryptophan is very hydrophobic, and when it is unfolded, then environment around this tryptophan is very hydrophilic. And the fluorescence property, because of this sufficiently high excited state time, the environment literally affects the fluorescence property, and hence fluorescence property of a tryptophan will be different when it is buried inside versus when it is open. And based on this marker, you can say exactly that whether protein is folded or unfolded, and hence, and that is why this fluorescence thing is an excellent method to study conformational change of protein or any other macromolecules like DNA or some other things. That's what makes fluorescence a remarkable marker to study all these things. But this method is not about. There are a lot to talk about fluorescence, but today I'm not going to discuss the fluorescence. I'm going to talk about fluorescence correlation spectroscopy, and hence I will be talking about less about fluorescence and more about fluorescence correlation spectroscopy. So, what is fluorescence correlation spectroscopy? So, as I said, that first I'll define fluorescence, then I'll define correlation, and then I'll talk about spectroscopy, which is a misnomer word. I'll just define it. So, having said that, this correlation. So correlation is in order to define correlation. Let's talk about density. Okay. So density is mass by volume. So mass and volume is always correlated thing. Okay. Like if you for a common matter, if you increase the mass, of course volume would increase. Okay. So these two things are correlated with each other. In the same way, if I say that but sometimes it's not. Sometimes it's not correlated. No. So let's talk about size and volume. Okay, size and mass. Okay, or volume or mass. So why it is not correlated? Size and mass is not correlated. Sometimes let's talk about somebody has come to your house with a big bag, and that bag has lots of clothes. Okay. And some foam and some lighter particles. So you would find that even the bag is of bigger size, the mass is less. And another thing is, let's suppose somebody has come to your house with a smaller bag, but the bag has stones in it. It will be different, definitely more heavier. And that is why size of a bag and mass is not very much correlated. Depends on what is there inside of it. Now, so correlation is something that one can define this way, but it's a mathematical term, and mathematicians use it to to find a pattern in any time series data. So like here, in order to define this methodology, I have to be a little bit detailed. I'm sure I'll not make you bored, but again, so there is always pressure that don't make statements that is confusing to common people or school kids. I don't know how much I'm confusing you, but trust me, even if you don't understand it, doesn't matter. Just listen to it, and you should get a flavor of things, that how the spectroscopy people work. I am a spectroscopy person. I work on this method. I just want to introduce the method so that you can get a flavor that how things work. Okay, so what happens here? Let's say you are looking at fluorescence and of anything. Of a fluorophore. So, in order to define fluorescence correlation spectroscopy, first I would like to show you the instrument, and then after that I will make you understand correlation. It will be easy. So let's go to the instrument that I am using it here. So this thing that you can see, this is the microscope. And microscope, a simple fluorescence microscope. So fluorescence microscope is something that gives you fluorescence, like like it's an obvious thing that it will give you fluorescence. But the thing is, how does it function? That's important. So in order to define how does it function, I will just open the system, and I'll show you how things work one by one. Okay. Okay, so here, so this whole setup has three parts. One is the source of light, which is laser in this case. Okay, so this box has certain things, and this is the LCU, laser combining unit, and it has different laser heads out here, and these laser heads. So laser is light amplification by stimulated emission of radiation. Okay, so stimulated using stimulated emission radiation, we produce laser light of a suitable wavelength. So the main advantage of using laser is that it is very much monochromatic, and it is linear. Intensity is very high, and you can, intensity does not decrease even if you take it to to the longer length. And when light from this light source, the laser source, when light forms of a particular wavelength, then it comes out through some optical fiber, and from that optical fiber light comes here, and there are multiple mirrors here, and through that mirror light comes here, and from here you see this kind of mirror light gets reflected, and these reflected light, then from here it goes inside this, and it goes here, and it comes up here. Okay, so just to show you that how does it function, I'll select a particular kind of light like this. There is an excitation shutter. I'll just press it, and then I will just open this shutter, and you can see that there is a light coming out here. One should not be looking at the laser directly from eye, but still you can see that here there is a excitation beam of light. It is of blue color. You can change it depending on what kind of fluorophore you are using. So some fluorophore get excited by blue light, some fluorophore gets excited by green light, some fluorophore gets excited by red light. So depending on that you can change the sample. Presently it is blue color, and then what happens that let's suppose that after that you put your sample. So there is a glass thing in which you can put your sample, some protein thing you can put here, or some fluorophore you can put here, and these light will excite those fluorophore present out here, and the fluorophore which you excite in this solution will definitely, as I explained, that it will give you some fluorescence, and that fluorescence will so fluorescence, so the particle, the fluorophore will give fluorescence in all the direction, but the fluorescence will be collected by, there is a series of lens just beneath it. Let me focus it. So there is a lens just beneath it, multiple lens, we call them objective. So that lens, collection of lens will take that fluorescence light, and again it will come through the same pathway, and here. So this dichroic thing, it just if you come from this side to this side, it will allow only fluorescence light to come here. And then there is a filter. See this thing. Okay, so presently there is no filter. So there are multiple filters out here. Filter is something that selects one particular wavelength of light and deselect another wavelength of light. So if we take, let's say we are taking some 539 35 light, the filter of 535, just to show it, 535 nanometer, filter for 535 nanometer. So if you go and search on your visible spectra, this 535 nanometer is the wavelength for green light. So only green light will pass through it. Okay, so if you see that everything will look green. So now it's looking like this, and if you put it, it will look green. Why? Because it is allowing only green light to pass through it. So all the white light is falling out here on this. Let's say you are looking at this box. So all the white light is falling on this box. But if you are looking through this, then only green light is allowed to cross through this filter. But sometimes you see that red thing is also coming. Like if you see like this, red thing is, so these are the reflected light. So if you are seeing the transmitted light, then it would look green. But if you bend it a little, and if this camera is getting the reflected light, then because of the intense since this energy of red light, the wavelength of red light is the highest, and that you can that can dominate in the reflected light. That's why you see red, but transmitted light will be green. So let's say we can put a filter out here. We can remove this filter, and we can put another filter out here. So only green light will pass through it, and then after that there are multiple things. So this is also a set of mirror that will change the path of the light, and then light will go here, and through this it will reach the detector. So these detectors works on the principle of, so these detectors detect the light which is coming here, and this detector works on the principle of photoelectric effect. So what happens? So light will fall here. There is a metal, and when light falls on that metal, electron will be ejected from the metal. More light will fall on the metal, more electron will be ejected from that metal. And then there is an anode and cathode. So here there is a cathode, and here there is anode. Okay, so what will happen? So and there is of course a potential difference, and you know that when there are electrons present between anode and cathode through a potential difference is essentially voltage, then electron will experience a kind of force. So electron experience a force which is equal to charge on electron and the electric field intensity, QE. So based on, and there are multiple diodes out here. What happens that electron will go from here to here, and there are multiple diodes, and they just amplify number of electrons. Like let's say 1000 electron ejected from the first cathode, and from it should be anode. Okay, it should be anode. Okay, so from first anode, electron will be ejected, and that let's say 10,000 electron falls on the first diode, and diode will amplify the electron into 1 lakh electron. It will fall on another diode. Diode will again amplify the electron into let's say 1 lakh electron, and then 1 lakh electron will fall on another diode, and that diode will amplify the electron into 10 lakh electron, and finally you will get basically current, and that current will be converted into some other signal. Okay, and that signal will be converted into some digital numbers, and that numbers you can get here in this software in the computer. So essentially this is how you measure the fluorescence. But one thing I didn't tell you about, something called pinhole. Okay, so what happens that when light comes from this thing again till here, okay, so then we select some small amount of light using a pinhole. Okay, so this is called pinhole. So this is called pinhole. Pinhole is nothing but a hole, a very 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 small hole that select light from a particular area. The hole is that small that you can't even see it. Okay, and it does not select. So here the beam width of beam is more. Okay, here the width of beam is more, and you don't want to select all the beam of light. You want to select only light which is coming from the focal plane. So focal plane will be inside the solution, which is not there right now, but we put solution here, protein solution, and if there are cells, then cells will be on the surface of this dish. So what happens that this pinhole selects a small volume in the sample, a very small volume. Now, now I will again go to the. I'll explain. I'll explain the correlation part after understanding all these instrumentation. Now it would be easy to make you understand what is correlation, and after that I'll define what is correlation spectroscopy, fluorescence correlation spectroscopy. Okay, so as I explained that there is a pinhole. That pinhole selects a small volume in your sample, and through that small volume there are molecules which come in. So in that small volume there will be molecules which is because of thermal energy, molecules keeps on diffusing as a rule of thumb, and what will happen that molecules will come in the observation volume and molecules will go out of the observation volume. So observation volume generally when we do the experiment, number of molecules in the observation volume is around 10 or definitely less than 100. That is something is needed, and when molecules come inside this observation volume, then you will see there is a fluorescence, and when it goes out of the observation volume, then you see there is no fluorescence, and hence fluorescence will keep on fluctuating. Okay, when fluorescence is coming, when molecules are coming inside the observation volume, more fluorescence. When molecules are going out of the observation volume, more fluorescence, and hence you will see a fluorescence fluctuation. Okay, now I will explain correlation part. What is correlation? So let's say you are observing some static molecule, okay, which is not diffusing freely. Okay, it remains in the observation volume forever. So will you see any fluctuation of fluorescence? No, you will see that there is a fluorescence, 10 unit fluorescence, and it will be at 1 second is one the same fluorescence, 2 second, 3 second, 4 second, 5 second, 10 second. So fluorescence value will remain constant until it gets photobleached. Photobleaching is a phenomena in which every fluorophore has can go to excitation emission cycle for a limited number of time. After that it does not go, it cannot go, and hence it becomes very much dead, fluorescently dead, and that we call the photo sample has got, or molecule has been bleached. Now the important point here that you will see a constant fluorescence if molecules are not going in or out. Second example, if you see bigger molecules, okay, and these bigger molecules cannot move in or out of the observation volume very fast. They will come slowly, they will reside in observation volume for some time, and then they will slowly go out. So what you will see that there is a fluorescence, and then when they enter, you see that there is more signal, fluorescence, and slowly when they go out, then you will see drop in fluorescence. Okay, and this is how again fluorescence will remain continue. Third example, if you imagine that in the observation volume, so in the observation volume there are smaller molecules, and obviously because diffusion, if you look at the diffusion coefficient of anything, so that depends on the thermal energy K beta T. So Kb is the Boltzmann constant, T is the temperature, and it also depends, it is inversely proportional to the molecular weight of hydrodynamic radius of that of that compound or that molecule. So K beta T by 6 pi eta r. R is the radius, eta is this is the Stokes-Einstein equation I am talking about. So Stokes and Einstein both gave a theory for diffusion, and that diffusion theory says that a particle diffusion coefficient, how fast or slow a molecule will diffuse from one place to another place, it depends on this hydrodynamic radius of the molecule. If the hydrodynamic radius of the molecule is more, then it will diffuse slowly. And it also depends on the viscosity. If a molecule is diffusing in honey versus water, then definitely molecule will diffuse slowly in honey because it has got higher viscosity, and the molecule will diffuse slowly faster in water because it has got a lower viscosity. Also, the diffusion coefficient depends on the temperature. More temperature, it will, the thermal energy will be more and molecules will, diffuse faster. So if third example I'm talking about, if there is a small molecules, then it will, diffuse inside the observation volume very fast, and it will leave the observation volume also very fast, and hence you will see the fluorescence fluctuation happening very fast. So three case, if molecules are stuck in the observation volume, you will not see any fluorescence fluctuation. Fluorescence will remain constant. If there is a big fat molecule which is diffusing very slow, then you will see that fluorescence fluctuation is happening very slowly. And if there are molecules which are diffusing very fast, then you will see that fluorescence fluctuation is happening very fast. Okay. Now, why am I telling you all these things? To make you understand the correlation part, because this is what correlation means. Correlation is a mathematical way to find the pattern in the data. So here the data is fluorescence, and you have to find the pattern. So pattern of what? That pattern of fluorescence fluctuation. If something is fluctuating fast, then correlation means what? So you say that fluorescence at time t1 and fluorescence at time t plus 1 second, fluorescence at time t plus 2 second, fluorescence at time t plus 3 second. That's all. And in all these three example, I will explain you what does correlation mean. So in an example where your fluorescent molecule is stuck in the observation volume, what you will see? You will see that your fluorescence fluctuation is not happening at all, and hence fluorescence at T1 and fluorescence at T1 plus 1 second, fluorescence at T1 plus 2 second will remain the same. It is not fluctuating. However, here I shouldn't say that the fluorescence at T1 plus 1 second, because 1 second is very high. The method I use in this time limit is less than millisecond. So I'll say like in millisecond. So if your molecule is not moving at all, it is stuck in the observation volume, then you will say that data remains correlated. Data fluorescence value is not changing with time. It is correlated. Okay, so whatever fluorescence is at T1, same fluorescence will be there at T1 plus 1 millisecond, same fluorescence will remain at T1 plus 2 millisecond, same fluorescence will remain at T1 plus 3 millisecond. Hence data remains correlated, means there is no change happening. That's what correlation means. Now second example, in which there is a big fat molecules and diffusing, or maybe same molecule diffusing in the viscous solution. So their fluorescence fluctuation will happen very slowly. So what will you say? That fluorescence at T1 is let's say fluorescence at T1 and fluorescence at T1 plus 1 millisecond. This two will be similar. Fluorescence at T1 plus 2 millisecond will be similar, but fluorescence at T1 plus 3 millisecond will be different. Fluorescence at T1 plus 4 millisecond will be different. Fluorescence at, so this is how you see that fluorescence level will be remain constant, and then it will become dissimilar. So data, the fluorescence value for slow moving particles, fluorescence value will remain correlated for some amount of time, and after that it drops down and it will again become some other value, and hence remain not correlated. Now if we talk about third example, in which your molecules are small and it's in a less viscous solution, temperature is high, it is moving very fast, then you will see that fluorescence at time T1 will not be correlated with fluorescence at T1 plus 1 millisecond, and the same thing will not remain correlated for T1 plus 2 millisecond. So mathematically, what do we do? That we correlate every microsecond. and personally I correlate every nanosecond for, fluorescence value. And what we see that initially it remains similar, and then as you increase the time, correlation drops, and it becomes no correlation at all. So what will happen if in three example I'll give you. If molecules are stuck in the observation volume, correlation, it is not dropping down. Second example, if your fluorescence value, if there is a big fat molecules diffusing in a viscous solution, less temperature, then data will remain correlated, and then low correlation, and slowly it will become very, correlation becomes zero. Okay. And if there is a molecule which is moving very fast, then you will see correlation, no correlation, no correlation, less, and this. So what you see that if molecule is not moving, not showing any kind of fluctuation, then it will go straight. If it is slow moving particles, then your fluorescence correlation value will drop down, but very slowly. And if your molecules are diffusing very fast, then your correlation value will be dropping down, but slowly, not very slowly, but fast. The correlation value will drop very fast. So what you can get out of it, if you fit it with some model, then you can get diffusion coefficient or diffusion time out of it, because it is the diffusion time that decides that how fast or slow a molecule will how fast or slow fluorescence will fluctuate. If fluorescence is fluctuating very fast, its correlation will drop down very fast. If fluorescence is fluctuating very slow, its correlation will drop down very slow. So that is how you can figure out diffusion coefficient through this methodology. I need to clarify this, that it is not only the diffusion coefficient that we can get out of this methodology. Any processes that can give you fluorescence fluctuation, any process that can give you fluorescence fluctuations, that process can be quantified by this method. What can be other possibility? So I'll talk about my thing, that what do I do. So let's say there is a protein, okay, and what I have done, that I have put one fluorophore at this position, and there is a tryptophan at this position, okay, let's say at this position, okay. Now what happens, that tryptophan has indole ring, and it is very much so these pi electrons, tryptophan would like to donate one electron to another thing, because it is very much electron sufficient. Okay, so what happens, and this there is a fluorophore. So when you excite the protein with a suitable wavelength of light, we are exciting this fluorophore by some 640 nanometer of light, and when we excite the fluorophore by 640 nanometer of light, the electron goes into the excited state, right? Now when the electron of this fluorophore goes in the excited state, the reduction potential of electron changes. The reduction potential of fluorophore changes. What is the reduction potential? Reduction potential is the ability to lose an electron, okay, so or gain on an electron, because it's reduction, okay. And when we excite the fluorophore using a suitable wavelength of light and electron goes in excited state, then reduction potential of this molecule changes such that it accepts electron from tryptophan, which is present out here, okay. Now this fluorophore can accept electron from tryptophan only when this tryptophan is in van der Waals contact with this dye, okay. So when they are in contact, you will see that the fluorescence, and what will happen when tryptophan donates electron to the fluorophore, the fluorescence of this fluorophore gets quenched, means this fluorophore will not give you any fluorescence, okay. So what will happen when this this tryptophan is in close contact, means in the van der Waals contact, which is in less than 1 nanometer distance, basically an electronic electronic interaction kind of thing, the distance at which you have an electronic contact. So when this tryptophan is in close contact with this fluorophore, you will see no fluorescence, and when they are apart, you will see fluorescence. Now protein molecules, everything is dynamic, everything is so damn dynamic. So as I said, that protein molecules are nothing but different amino acids linked with each other by covalent bond, and these covalent and these things gets folded, and even in the folded state, protein molecules do this breathing motion. Okay, they keeps on doing this this breathing motion. So breathing motion means, or we call this conformational dynamics, means protein keep on doing this conformational dynamics. In order to explain this, let me introduce, so I'll come to this thing again, that how can we use this method to understand not only diffusion but other molecular phenomena that can be used to to study other photophysical phenomena. So anything that can give you fluorescence fluctuation, either it is diffusion, either it is dynamics, anything that underlying principle you can identify by this methodology. Now but I'll come to this thing. I have to make you understand what is this protein dynamics. So if you are aware of Koshland induced fit theory, it says that how does enzyme and a ligand bind. So it says that there is a ligand and there is an enzyme. Enzyme is essentially a protein molecules which works as a catalyst by lowering the activation energy barrier. So that is another theory. But here Koshland induced theory says that how does an enzyme and ligand bind. It says that when a ligand comes and it interacts with enzyme, and when it binds with an enzyme, so there is a release of energy. Okay, that we call it binding energy, and this binding energy changes the conformation of protein such that it gets tightly bound to the ligand. Okay, this is the basic Koshland induced fit theory that you read in all your textbooks. But lately there is another theory, we called it conformational selection theory, which is explaining the same phenomena but in another way. And we have a lot of evidence now for conformational selection theory. It says that no, it is not the binding of ligand that is converting the conformation of protein molecule from conformation A to conformation B. As I said, that there's ligand comes and binds to protein, and this is the binding, and when bonds form, so when bonds form, there is a release of heat, and that enthalpy, the binding energy, changes the conformation such that it binds with the ligand very efficiently. Conformational selection theory says no, this is not happening. What happens that this conformation and these conformations already exist, means protein already exist in two different conformation A and conformation B. And when these two conformation is in equilibrium, let's say that 80% or 90% is in conformation A and 10% is in conformation B. When ligand comes and preferably bind to one conformation, let's say conformation B, and the binding of ligand with conformation B lowers down the free energy of this conformation B ligand interacted thing, and when ligand binds with the conformation B, the equilibrium which was already existing between conformation A and conformation B, it just shifts towards conformation B. So it is not the binding of ligand that is converting protein into another conformation B, but rather protein already exists in two different conformation and it keeps on visiting each other. The binding of ligands just shifts the equilibrium towards another conformation. but it is important to understand that these two conformation already exist. What does it mean? If a same molecule exists in two different conformation, it essentially means that there is a free energy barrier between these two molecules, and these two molecules keeps on visiting each other depending on the height of free energy barrier. So molecules will be in this conformation as well as in this conformation. This conformation is as well as in this conformation. And how fast or slow this movement is happening, it depends on the free energy barrier between two different conformation. Let's say this motion is very fast. It essentially tells you that the free energy barrier between conformation A and conformation B is very slow. And let's say it is happening when it is moving when this conformational dynamics is happening very fast, it essentially means that free energy barrier, height of free energy barrier is small. That's why it keeps on, if there is a smaller free energy barrier, it can visit each other very fast. And if the free energy barrier is big, then the molecules will do the show the conformational dynamics very slowly. Okay. So so if you want to, so today, now I want to understand this conformational dynamics of protein. Okay, so what did I do? I put one fluorophore here and one tryptophan here, and when this happens, then you see that when this happens, no fluorescence, because this tryptophan quenches the fluorescence of the fluorophore by donating one electron, something, the phenomena we call photo-induced electron transfer. And when this molecules keep on doing this motion, then you will see fluorescence fluctuating. Now why would fluorescence fluctuate? Simply because when in this conformation, no fluorescence, in this conformation, fluorescence, no fluorescence, fluorescence, no fluorescence, fluorescence, and hence you will see fluorescence and no fluorescence. And so let's say if a molecule remains in a fluorescent state for a longer time. So now I'll take another two example. So this is one protein molecule and this is another protein molecule. Same setup but two different molecule. Now if this molecule is doing the conformational dynamics very slowly, so what will happen? Let's say I'm talking about the microsecond time scale. So what will happen? Let's say this protein is showing dynamics in microsecond time scale and this protein is showing dynamics in nanosecond time scale. So if what will happen? So there will be fluorescence, no fluorescence, no fluorescence, fluorescence. So what will happen? Whenever there is the same fluorescence, you will see the fluorescence value remains correlated with each other. Okay, and hence this fluorescence decay, correlation decay will happen slowly for a protein which is showing you the slower conformational dynamics. For a molecule which is showing slower conformational dynamics, their correlation value will drop down very slow. Okay, and if a molecule is showing very fast conformational dynamics, their correlation value will drop down very fast. Okay, so this is how it's not only diffusion that you can monitor by fluorescence correlation spectroscopy, but you can also monitor the dynamics of protein, conformational dynamics of protein. So, and not only conformational dynamics of protein, but many more things like aggregation, like interactions, like assemblies, all these things. Any phenomena that gives you any fluorescence fluctuations, underlying principle can be monitored by this process that we call fluorescence correlation spectroscopy. Now, third point is spectroscopy. Nothing to talk about. Spectroscopy is a misnomer word. As I said, that spectra is we call something a spectra when you monitor at different wavelength. When you say absorption spectra, you must have seen in your textbook that absorption spectra is on x-axis you have different wavelength, and on y-axis you have intensity, like how much intensity means how many photons are there coming out from that molecule. So spectra, we call something spectra when we are monitoring this thing at same at different wavelength. But here in fluorescence correlation spectroscopy, we monitor things at the same wavelength, at one single fluorescent wavelength. That's why sometimes it's misnomer to call it spectroscopy, but people have named it, so we have to respect them. So people who gave this fluorescence correlation spectroscopy methodology are Magday, Ilson, and Webb. So Webb passed away, 3-4 months back, and I just I'm a big fan of that person, Ward W. Webb, and he introduced this method. And not only this method, he works on semiconductor, he worked on brain, neurotransmitter, he worked on you name it, any principle. He gave multiphoton microscopy, Raman spectroscopy. He worked on a lot of areas, physics, chemistry, biology, and he passed recently. It's a big loss in scientific community, but yeah, this is how things work. Nobody lives here for eternity, because death is favorable. As I said, that thermodynamically a higher entropic state is more favorable, and death is favorable. Life is not very much favorable. In order to revert life, you have to do in order to revert the death, you have to do a lot of things, and ultimately this body, my body, your body, and everything order, they will gain the disorder and it's more stable state. But in order to maintain this ordered state, we continuously provided food. If it is plant, they provide energy from sun, by photosynthesis. If it's about us, in order to maintain this ordered structure that we call body, we eat a lot of food. Thank you.